When we say the electronic charge, we mean the charge on an electron, or the charge on a proton. Hopefully you know that the magnitude of charge on a proton is equal to the magnitude of charge on an electron, except one of them's positive, one of them's negative. We've just arbitrarily said that electrons are the negatively charged ones and protons are the positively charged ones. We could have equally well said that protons were negative and electrons were positive. In any case, the charge in coulombs, that's what this capital C stands for, the charge in coulombs on any electron or any proton is this number here, 1.602 times 10 to the negative 19th coulombs. In chemistry, charges are expressed as unitless multiples of this value, not in coulombs. It's very much easier to say 2 plus, as in calcium 2 plus, and not 2 times 1.602 times 10 to the negative 19th coulombs. We often don't use this number in a lot of what we're doing in first year college level chemistry, but the charge on a proton, the charge on an electron, is that number right there. An atomic mass unit, abbreviated AMU, is used to measure masses of atoms and subatomic particles. I don't require that my students know the rest masses of the proton, neutron, and electron. I do require that my students know that a proton has a mass of about 1 AMU, as does a neutron. You can see that an electron is much less massive than either protons or neutrons. It would be a good idea to memorize that the mass of a proton is approximately equal to that of a neutron, and that is approximately 1 AMU. Here's another conversion that you should, check it out in the lower right, memorize. 1 gram is equal to 6.02 times 10 to the 23rd atomic mass units. Many of you will recognize that large number, 6.02 times 10 to the 23rd, as Avogadro's number, but you can see that an AMU is a very tiny unit of mass because it takes a whole bunch of them to give you 1 gram. Angstroms, which is abbreviated with a capital A with a little oval or circle on top, angstroms are often used to measure atomic dimensions. An angstrom is 1 times 10 to the negative 10th meters, or 1 times 10 to the negative 8th centimeters. An angstrom is not an official SI unit, but it's still used sometimes, so it wouldn't hurt to know that conversion between angstroms and meters. Of course, when we mean the atomic number, we're referring to the number of protons that an atom has. It is, of course, the whole number on the periodic table, and it determines the identity of an atom. However many protons the atom has, just by looking at that, we know what type of atom it is. The number of neutrons, could vary. Number of electrons, could vary. But if you know the number of protons, you know what type of atom you have, period. The mass number is the sum of the protons plus the neutrons. So the mass number for an atom is how many protons it has plus how many neutrons it has. We don't add the electrons in to the mass number because electrons don't hardly have any mass. And we simply take protons plus neutrons because a proton weighs the same, roughly, as a neutron, 1 atomic mass unit each. Isotopes are different varieties of an element's atoms. They have the same number of protons, but different numbers of neutrons. And for that reason, they of course have different masses. Some isotopes are radioactive, others aren't. If an atom has the, quote, right number of neutrons, it's not radioactive, it's stable. If that atom has not enough neutrons in its nucleus, or too many neutrons in its nucleus, then it's unstable or radioactive. A nucleus of a specific isotope is called a nuclide. And finally, all atoms of an element react the same chemically. If I consume stable carbon-12 and, let's say, some radioactive carbon-14, my body doesn't know the difference. My body says a carbon atom is a carbon atom. I'll integrate it into the cells, no problem.